This is SpaceTime, Series 26, Episode 63, for broadcast on the 26th of May, 2023. Coming up on SpaceTime, discovery of a potentially volcano-covered Earth-sized world. Computer simulations show us where the first quasars may have come from. And that stuck antenna aboard the Jupiter-bound JUICE spacecraft has finally been freed. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered an Earth-sized exoplanet, that is a world beyond our solar system, that may be carpeted with volcanoes. A report in the journal Nature claims the planet, known as LP791-18d, could undergo eruptions as often as Jupiter's volcanic moon Io, the most volcanically active body in the solar system. LP791-18d orbits a small red dwarf star about 90 light-years away in the southern constellation Crater. Astronomers found and studied the planet using data from NASA's TESS Transiting Exoplanets Survey satellite and the Spitzer Space Telescope, as well as a suite of ground-based observatories. LP791-18d is slightly larger than the Earth, and it's tidally locked, which means the same side of this planet always faces its host star. In the same way, the Moon's tidally locked to the Earth, with the same side of the Moon, the near side, always facing us. Now, for this planet, however, that means the day side would most likely be too hot for liquid water to exist on its surface. But the amount of volcanic activity all over the planet could sustain a significant atmosphere, and that would allow water to condense on the night side. Astronomers already knew about two other worlds in this system, LP791-18b and LP791-18c. The inner B planet is about 20% larger than the Earth, while the outer C planet is about 2.5 times the Earth's size and more than 7 times its mass. During each orbit, planets D and C pass very close to each other, and each close pass by the more massive planet C produces a gravitational tug on planet D, making its orbit somewhat elliptical. Now, on this elliptical path, planet D gets slightly deformed every time it orbits around the star. These deformations create enough heat through internal friction to substantially heat the planet's interior, producing volcanic activity on its surface. Jupiter and some of its other moons affect the Jovian moon Io in a similar way. Now, what makes all this even more interesting is that planet D sits on the inner edge of the star's habitability zone. That's the area around a star where liquid water, essential for life as we know it, could exist and pool on a planet's surface. Planet C has already been approved for observing time on the James Webb Space Telescope, and astronomers think planet D is also an exceptional candidate for atmospheric studies by the James Webb mission. One of the study's authors, Jesse Christensen from NASA's Exoplanet Science Institute at the California Institute of Technology in Pasadena, says one of the big questions in astrobiology, the field that broadly studies the origins of life on Earth and beyond, is if tectonic or volcanic activity is necessary for life. After all, we have both here on Earth, and we have life, but it's also the only example we have. In addition to potentially providing an atmosphere, these processes could churn up material that would otherwise sink down and get trapped in the crust, including those which we think are important for life, like carbon. It's also worth noting that Spitzer's observations of the system were among the very last the Space Telescope collected before it was formally decommissioned in January 2020, a fitting end for an historic mission. This is SpaceTime. Still to come. New computer simulations show us where the first quasars may have come from, and that stuck antenna on the JUICE spacecraft has finally been freed. All that and more still to come on SpaceTime. Amazing new computer simulations have shown astronomers how massive streams of primordial gas in the very early universe could have created supermassive black holes without the need to first form stars. The findings, reported in the journal Nature, could explain how so many quasars may have formed in the very early universe. Quasars are powerful jets of energy and matter generated by material being ripped apart as it falls into supermassive black holes. They're among the most distant objects ever seen, shining in the dark, often more than 13 billion light-years away. And that places them quite literally close to the dawn of time itself. Physics tells us that the black holes which generate these ancient, powerful quasars had to have been enormous. And observations have confirmed the existence of supermassive black holes with more than 1 billion times the mass of our Sun existing just 700 million years after the Big Bang. And that raises an important question. How could something so big have formed so early in the universe? And that's where these new computer simulations come in. Astronomers using computer modelling are starting to get a glimpse of what the formation of these dark behemoths may have looked like. One hypothesis involves lots and lots of giant stars, hundreds or more times the mass of our Sun. Now, being so massive, these stars burn through their nuclear fuel supplies really quickly. They live fast and they die young, collapsing at the end of their lives to form lots of stellar mass black holes, which could then merge together, forming ever larger black holes, eventually getting big enough to form the supermassive black holes we see today. But there's just not enough time to do that. Another idea involves giant stellar clusters of stars. These contain hundreds or even thousands of stars, all in tight, closely packed balls. And these too would eventually collapse at the end of their lives to form hundreds of thousands of stellar mass black holes, which then merged into a single black hole. Problem is, even if you ended up with a black hole 100,000 times the mass of the Sun, that still doesn't equate to the billion solar mass black holes being observed in the early universe. There's still just not enough time to do it. However, what about eliminating the star altogether, and instead have the dense and pristine molecular gas clouds from which the stars are made collapse directly to form a supermassive black hole? Now, this isn't possible today because of the expansion of the universe over the past 13.8 billion years. But go back more than 13 billion years and the cosmos was physically smaller, more compact, and so it could have been possible. However, the calculations for such massive implosions are incredibly delicate. After all, what's to prevent pieces of gas cloud from cooling and collapsing under their own weight and forming stars, just as star-forming clouds in the modern universe do? Some astronomers suggest that ultraviolet emissions from nearby newborn stars may have heated these massive gas clouds just enough to keep things moving too fast for molecular hydrogen to form. And it's the molecular hydrogen which collapses down to form stars. However, other astronomers have argued that such specific requirements would make the process too rare to explain the number of supermassive black holes that they've already found in the early universe. The new computer simulations, which are rebuilding the conditions of the infinite universe when it was just 100 million years old, followed the growth of a small frothing sea of matter fed by torrents of inflowing gas. The simulations showed that the streams were not only dense, but also very fast-flowing, rushing in at speeds of 50 kilometers per second. That's over 160,000 kilometers an hour. Or to put that another way, they were carrying up to 10 suns worth of material each year. The computer simulations showed that the sea at the center of these streams of material grew very quickly, and within the sea, eventually a clump would take shape, then another. But the turbulence of the inrushing gas keeps these massive clumps from collapsing straight away into stars. Instead, the clumps simply continue to get bigger. By the end of the simulation, these clumps contain tens of thousands of suns worth of mass. Now, eventually, these clumps would compress into what the researchers called supermassive stars. But following their evolution requires a different kind of computer simulation, one that takes stellar physics into account. Now, these stellar monstrosities don't last long in these simulations, usually just 2 million years or so, before they also collapse into black holes, but monster ones between 30,000 and 40,000 solar masses respectively. Jonathan Nally, the editor of Australian Sky and Telescope magazine, said such massive seeds could easily collect more gas and grow to become the dark monster black holes, generating the quasars seen by astronomers today.
Well, quasars, it's a funny word, Quasar, and it stands for quasi-stellar object, because when they were first spotted by big professional telescopes, they just looked a bit like stars, right? But it was soon realised when astronomers worked out what their redshifts are, that they couldn't possibly be stars, because they're so far away and so far back in time that at those distances, individual stars would be simply invisible. But these things, to be that bright, that far away and that far back in time, must have been very, very, very bright. What on Earth, but what in space could possibly produce that amount of energy in what seemed to be a fairly condensed area, like a small area, a small volume, back then in the distant reaches of time, back towards the Big Bang. So, they called them quasars, and they're obviously around in the early universe. Couldn't be stars, far too big and bright for that. So the consensus formed was that the only thing known that could produce this kind of energy was the black holes. Now, black holes themselves don't give off that kind of energy, but any gas and stuff that is swirling around near them, as it speeds up, it will give off a lot of light, and that's what we would be seeing in the form of these quasars. But to get that sort of amount of energy, these black holes would have to be super duper big. Not the sort of small black holes you get when an individual star goes bang at the end of its life and its core compresses down into a tiny thing. These would have to be black holes that weigh, at least thousands of times the mass of our sun. So they were big, huge black holes. So scientists have now done some computer simulations looking at what would have happened to the gas clouds that they think populated the early universe. And their calculations have shown that clumps would form within these clouds, but instead of these clumps going on to form individual stars, the clumps sort of joined together and they just kept growing and growing, getting bigger and bigger like Topsy. And when they became big enough, some of these clumps joined up and then their combined mass made them gravitationally collapse into very big black holes. This is what was happening in this computer simulation, right? So there all of a sudden you've got big black holes, very big black holes, and there would still be remnant gas going around. So that gas would be sort of sucked in towards the black holes, start swirling around, and the faster the gas goes, the more light it gives off. And bingo, you've got a quasar, and lots of quasars. Their calculations show that you would get lots of quasars. And this is really early on in the age of the universe, not long after the Big Bang in sort of space terms. So this could explain why you would have quasars, which are thought to be powered by big black holes, fairly early on. It would be these big gas clouds forming individual clumps, and the clumps just joining together and eventually collapsing from their own gravity and becoming big black holes. So interesting stuff. With the James Webb Space Telescope up there now, with its view optimized for infrared, which is going to be brilliant for looking back through the age of the universe back towards the Big Bang, we should start to get some really good imagery and data of what was going on there, better than we've had so far. So we may be able to confirm or refute this hypothesis from this computer simulation. So again, we're living in a really exciting time. We've got the technology out there, and hats off to the people who make these telescopes and design the things and run the missions, because it's just going to answer these questions. So these scientists have done computer simulations, calculations of what might happen. The telescope out there, James Webb, is going to show us what did happen.
For the last 50 years, one of the big debates in astronomy has been which came first, the supermassive black hole at the centre of a galaxy or the galaxy. It sounds like this computer simulation has reached a conclusion.
Yeah. Well, if it's correct and if it can be verified, then maybe the black holes were the sort of the seeds or the nucleus that then gathered in material around and which then formed this swirling galaxy, these beautiful galaxies that we see. As I say, the James Webb Space Telescope is going to be able to show us these things, at least in some detail. So we'll be able to verify or refute this particular idea or any of the other ideas that have been proposed over the years. So it's exciting time.
We just had the announcement of the discovery of Glass Z12, which is possibly the earliest fully formed galaxy ever seen, just 300 million years after the Big Bang, which means the stars would have started forming just 100 million years after the Big Bang, which means the cosmic dark ages were really short. They only lasted 100 million years before the epoch of reionization.
Yeah. So evidence is sort of accumulating, you might say, that things got going really quickly in the early part of the universe. And this is the great thing about science is that, we had, for all these years, we've had a certain amount of data, we've had certain observations, and we couldn't get anything better. So people have had to form hypotheses based on that. But, we get more data, and we've got more observations, bigger and better telescopes that show us more clearly what exactly was happening. And that way you can sort of drop off the hypotheses that don't match it, and the hypotheses that do match, well, one of them may end up being right. It's a sort of that's the process of scientific discovery, really.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And this is SpaceTime. Still to come, the European Space Agency successfully frees a crucial antenna that was jammed in a semi-stowed position aboard its due spacecraft. And later in the science report, a new study confirms that using cannabis during pregnancy can impact the growth of the baby. All that and more still to come on SpaceTime. The European Space Agency has successfully freed a crucial radar antenna that was jammed in a semi-stowed position on its JUICE spacecraft. Mission managers in Darmstadt, Germany freed the 16-metre-long antenna following a month-long effort. ESA's Jupiter Icy Moons Explorer, or JUICE mission, was launched aboard an Ariane 5 rocket from the Kourou spaceport in French Guiana back in April. It's on a decade-long voyage to study the Galilean ice moons of Jupiter, arriving there in 2031. The crucial radar antenna is the heart of its science program. It'll peer deep beneath the icy crusts of Europa, Ganymede and Callisto, all of which are suspected of harbouring deep subsurface liquid water oceans. Europa alone is suspected to contain more water than all the Earth's oceans combined. However, soon after launch, a tiny protruding pin refused to move, preventing the antenna from fully deploying. Mission managers tried shaking and warming the $1.8 billion spacecraft in order to get the pin to budge, and a bit of back-and-forth jolting finally did the job. ESA says all other systems aboard the spacecraft are operating normally, with the radar dish, solar panels and 10.6-metre magnetic field probe all deploying successfully. The 6,070-kilogram bus-sized spacecraft will undertake a series of gravity-assist flybys of the Earth, Moon as well as Venus in order to reach the Jovian system. Eventually, JUICE will go into orbit around Ganymede, becoming the first spacecraft to orbit a moon other than the Earth's. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. New researchers confirm that using cannabis during pregnancy can impact the growth of the baby. The findings, reported in the journal Frontiers of Pediatrics, show that even when marijuana is used only during the first trimester of pregnancy, birth weight was reduced by around 150 grams. The studies also showed that babies exposed during the entire pregnancy were nearly 200 grams lighter, and their head circumference was nearly a centimetre less than babies who had not been exposed. The authors say these findings are important because newborn size is one of the strongest predictors of later child health and development. Scientists have released the first draft of a reference pangenome, a collection of DNA sequences from 47 people which better reflects the diversity of the human population. The findings, reported in the journal Nature, can be used as a comparison tool to study genetic disorders and other human DNA sequences. To understand the differences that make humans unique, scientists create a reference genome sequence, which other DNA sequences can then be compared to. But until now, the standard reference genome was always limited in its ability to reflect human diversity. That's because it was based on the DNA of just 20 people, and most of it came from just a single person. The new pangenome reference includes genetic sequences from 47 people from the first ancestries, and the researchers are hoping to increase that number to around 350 by the middle of next year. As the human population continues to grow beyond 8 billion at an alarming rate, a new study shows that nearly 2/3 of native elephant habitat has been lost in Asia since the 1700s. The findings, published in the journal Scientific Reports, shows that across Asia, about 64% of the land suitable as a habitat for elephants in the year 1700 is now gone. The authors base their findings on land use change data spread across 13 countries in order to identify land that 300 years ago would have been suitable for elephants to live on. Scientists found mainland China, India, Bangladesh, Thailand, Vietnam and Sumatra have all lost more than half their suitable elephant habitat. The researchers say this drastic reduction in places elephants can live could be driving conflict between them and humans. A new study reported in the journal Psychopharmacology has found that people with a history of using psychedelic drugs can have long-lasting beliefs in the supernatural, non-physical worlds. The findings revealed significant increases in beliefs related to mind-body dualism, paranormal activities, and spiritual phenomena. However, Tim Mendham from Australian Skeptics says, instead of acting as a warning, the authors suggest the findings show the potential use of psychedelics as a therapeutic intervention.
They found that if you had taken drugs in the past, and if you sort of take it again like a psychedelic drug in the past, and if you take a little dose even now, years later, you'll find that there's lasting belief about the supernatural or the non-physical world. And this has various sort of manifestations from talking to the trees. Mind and body are separatable. This is like out-of-body experience. The paranormal is true, various things like that sort of people who have been at one stage taking drugs and can come back to it, and these attitudes will revive very quickly. So they're talking about a component of psychedelic drugs which is psilocybin, which can cause immediate mystical experiences and long-lasting improvements in an individual's spirituality. Now, I don't know what an improvement in spirituality is. Maybe they increase in spirituality. Maybe they have greater feelings of sort of one with the world, etc. I don't know. But they're saying that even so, it hasn't been that studied that much. Is something that people can look at. But to suggest that people who have gone through psychedelic drug use, and that can include LSD or natural psychedelics like, I think, peyote and that sort of stuff, ayahuasca.
Magic mushies, that sort of thing.
Magic mushrooms, that sort of stuff. There's a whole range of them, created in a lab or grown in a glass house, that they create a psychedelic effect that certainly affects your perception and your understanding of things, and in some cases it can have a very long-lasting, even permanent impact on the way you see things or what you do see, and whether that's an improvement in your...
They like to call it expanding your mind.
Yes. Tune in, turn on, drop out. But it's sort of like almost like a bit of a no-brainer. That's the reason you take psychedelics. That's the reason you take psychedelic drugs, is to actually expand your mind, actually to see different things, to see the world in a different way. Now, whether that's a better way or not depends on whether you have a good trip or a bad trip. And anyone who's dealt with people who have been in those sort of circles know that can be either way. You can't predict it, and sometimes there's no trip at all. So therefore, to suggest that these have long-lasting effects is not particularly new, but what they are saying is that this is an area for further study, which is basically what every research project says at the end. What we need is more study, give me a grant.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies. Or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.